First of all, I'd like to once again thank the organizers for organizing this conference. And I've heard, I did not attend the last one, but what I heard is that this conference looks much bigger than what it was for the past few events before. It gives me a really good positive vibe that I think Taiwan as a whole is on the cusp of something happening big in geothermal. You all have done small strides. A few megawatts have been installed already. But what I'm looking forward to, based on what I see here in terms of the attendees, both from the private sector, the government, investment, that Taiwan is looking at something much bigger than what we planned. And yesterday when I was talking, we told about a 1.2 gigawatt in 2030. And always a question is asked, is it achievable? I think with what we have in plans, and also with a very stepwise approach, learning from things that others have done and have failed and have improved on, plus the technology that we have available now. And that's what I'll be sort of discussing today to give you a small insight of what we can see in the current scenarios rather than what we have done in the past. Especially in the past, if you see globally, wherever geothermal has been installed, right from my hometown in New Zealand, where we started back in 1958. In US, it's been a little bit older than that. Go to Italy, it's been 1900s. The rate of change has been quite slow, gradual, I would say. But I can say one of the countries was Kenya, which from 1990 onwards, we were at a very slow pace. And from about 2000 onwards to about 2025 as we speak, we've grown from almost 100 megawatts being produced to about 1,000 megawatts. So that's almost a 10-fold increase. Those have been done with challenges that we had, especially for example in Kenya where we did not have much of oil and gas expertise. Now when I try that to Taiwan, yes, you all have got some expertise in oil and gas and other things that you have done in the past, but we sit in a region which is of prime focus to be thought about. The prime focus being places like Malaysia, Indonesia, and other places where oil has been done pretty well. I think we can take learning steps from them in terms of equipment and technology. Now, let me focus now on to my topic, what is, how do we pick a spot? I'm sure there are many geologists in the room over here, may not agree with me totally, but I look at it from an aspect where how can we make our choices more precise, avoid drilling dry holes. Yes, we do come across dry holes, but that may not be the end of it, especially when we talk of EGS and AGS. Why do I say that? We used to have holes that would be dry in a hydrothermal environment. But, for example, everybody talks of EVER or FERBO. Some of the projects that were done at FERBO, one of the first projects in Nevada, I had drilled those wells back in 2010 for a hydrothermal resource. And what happened there is, we were drilling those wells and we did not get what we expected in terms of the megawatt output. But now you see, about a decade later or 2 decades later, those same wells are being now looked at from a very different goal of, yes, there is heat, there may be less fluid or steam movement, but the heat that was there has been utilized by FERBO and now they're generating power from that. So everything is not dark and gloomy. You have a sweet spot over there. Now, you all can read this later, it's just a disclaimer, I have to put it on. Now, my topics today, I would like to focus on a few things. One is conventional geothermal resources, how do we look at those? Then you see, now we've got the two other new terms that have been coined: enhanced geothermal systems and advanced geothermal systems. The third thing is large-scale screening methods. Fourth, what are the tools that we have currently in our toolbox? And I'm sure some of you who are listening to me may be developing your own tools. I'm certainly sure that those tools, like NREL has been doing that back in the US, in the national labs space, what they're looking at is developing new tools. The reason being, can we, rather than playing a lottery game, can we make our choice of a drill site more viable? And last of all, how do we improve our success ratio? I just focus on that last thing before I forget. Why is success ratio so important? When we drill these type of wells, for example, yesterday you will have heard a conventional geothermal well down to a depth of about 2,500 meters is anywhere in the range of about $6 million per well. There may be people who may say that, Sam, we can do it faster or cheaper. I've drilled myself wells for the last 3 decades. Doing faster and cheaper is a way to spread it out, the cost. But, as I said, everybody can drill a hole in the ground. But drilling a well in the ground is a totally different story. So now, when you talk of improving success ratio, some of these wells, you are spending $6 million per well. And nowadays we are talking of, in EGS projects, you're talking of doublets. So you've got to drill 2 wells almost to the same depth, directional. So that takes a lot more of cost and your targeting. When you talk of your success ratio improvement, you look at $12 million being spent on a well. What do you want to be the final outcome? I do not want to drill a dry hole or not achieve what I wanted. So here comes the challenge. How can I improve my success ratio in order to make my $12 to $15 million well spent? Number one. Number two is spending the cost on, one is drilling that well. The second part of it is, how do we get what we need, what we are looking for? In terms of geothermal, we are mainly looking for heat. And some of the hydrothermal prospects, even in Taiwan that we have, we are looking for a resource also in terms of either steam or hot water. So some of you all might have seen this drawing, this slide yesterday, but I'll talk of it from a different aspect today. If you go from this side, from your left side to the right, you first see on the left side, you see the supercritical. This has been done in the past. What have they done here is you are actually drilling into a resource itself. And if you want to talk of drilling into lava, that's one of the most challenging things that you have done. We've drilled in the world so far, we have drilled into lava in 3 places. One is Hawaii, one is Iceland, and one is Kenya. And I've had the privilege of working in all 3 places. Especially in Hawaii, Gad is here, he speaks about Ormat. That's where we drill into, we actually drill those wells in Hawaii about 11 kilometers crow flying distance from the Kilauea volcano. And recently, in the past about 3 years back, we had a volcanic eruption that actually came very close to our plants in Hawaii. That's where you're drilling into supercritical fluids, magma coming to surface. Now, how do you control that? That's number one. And number two is, how can we use that supercritical steam to generate better efficiency in terms of steam? That's got its own challenges. One of the challenges, that brine. It's a very corrosive brine, number one. Number two is the heat. What happens with heat? Your metallurgy gets affected quite a bit. In terms of drilling, I would say, you actually have expansion and cooling. So that's something to be thought about. The second one is what we talk of, the normal geothermal wells where we are not drilling into supercritical steam, but yet we are looking for a resource that has got steam or hot water, and how can we bring that to surface? Those two, we know that there has to be permeability, and sometimes when we talk of permeability, as a geologist, you may say, what do you mean by permeability? Oil and gas, we used to talk of porosity. Geothermal, don't even talk of permeability. I am talking of fractures, and some of the lava tubes are so big, like you can come to Hawaii, you can see, you can actually walk through those lava tubes. That's your resource that you're looking into. Now come to the third one, EGS. Now EGS, the new term that's been coined, what we are looking for there is heat, but we may or may not have the hot water or the steam that drives it. Then you come to AGS, where you're almost replicating that system but in a closed loop. So that there, your well, your fluid that's inside the closed loop is not going to be in contact with any other fluid outside. And the last of all, on the extreme right, you see direct use projects. Now, many times in different countries, you may not have the super hot or the high temperature fluids, but you may have fluids that are about, say, 100 degrees centigrade. Can we make any use of that? Yes. And those are going to be very critical because, say, in some of the countries that I visit, say, like work in Dominica, in the Caribbean islands, once we went and we saw that, or in Kenya, where heat is used, the carbon dioxide is sent across to the rose-growing greenhouses, and the hot water is used to keep the temperature regulated. Same thing happens in Iceland. So again, if you've got a temperature of a resource that is not over 100 degrees or 150, yet you can use them very viably. Now, to focus on my talk was, what are the exploration tools that we currently have that we can look forward to using for these type of methods? First of all, when we try to look at, from a Halliburton perspective, when we look at these type of projects, we first try to delineate, say if you think of Taiwan as a country itself, we look at the island of Taiwan as a whole. We get a lot of data from satellites that pass over you. Every day there are satellites moving across and they are gathering data. For example, what are the data that they gather? They give you shallow heat temperatures, or across as it flies over Taiwan, it will be gathering data on which are the areas that have a higher temperature gradient than other places. For example, number one. Number two, it would look at alteration mineralogy. Number three, it would look at stress and strain of faults that can be probably mapped. And looking at those, we are trying to delineate from the whole island of Taiwan to a few specific hotspots. So once we do that, then we go into details on choosing out of the hotspots. Now, why is this very important? This is quite important because if you were to drill, if somebody was to tell me, Sam, come and look for the best spots in Taiwan, and they tell me, Sam, go and drill all along the island of Taiwan and see which is the best spot. It's going to be economically not feasible, number one. Number two, is going to be a large scale, extended period of time where you would have to do that. Now, to reduce that time effect, that time and the cost, what you're trying to do is use existing data, average, and also imagery, satellite image and other things to cut down that time and the cost. Once we have done that, then we also look at wells that may have been drilled. So when you look at wells that have been drilled in Taiwan, it could have been done for oil and gas. So what we do, for example here, we take that data and also put that into the model. Finally, what are we looking at? We try to come up with a conceptual model. This model gives us a basic idea of what is subsurface. That's where the geologists, like those who are listening to me, like to tell me, Sam, this is where I want you to drill. So keep that in mind. Now, Once we do that, then we go into this workflow. So what you look at is, you look at the 3 Gs, geology, geochemistry, geophysics. Then you look at any petrophysical. So what happens there, after you're done all your satellite imagery data gathering, finally you have to get some boots on the ground. You go and sample springs. You go and look at geology that is there. Based on that, you come up with what does it look like subsurface. So that's where we come up with the conceptual model. Once we do the conceptual model, here comes some important things. We look at analogs of the same type in different parts of the world. Can we use those to, again, look at our criteria to make those changes? Then we look at how do we develop this resource. Because keep in mind, yesterday we did speak about this. Geothermal resources, when you sign a PPA, you're signing a PPA for 20 to 30 years. So this resource has to be managed properly. And last of all, the risk analysis. We spoke yesterday widely from different audience we heard, speakers we heard this. The risk that is there, how do we mitigate the risk and minimize it? Once we can minimize the risk, that helps us to get our deliverables better. And that also helps with the last thing here is well engineering. What Halliburton, we've got a team called Neftex, which does all the initial data. Then comes our landmark team, which does both well engineering, well placement, and execution of these wells. Now, here's a quick screenshot. I won't go too much detail because I mentioned about this. You all can have a look at this when you get chance. And if you all have any questions, please reach back. I'm just giving you a small example of what we have done, for example, on looking at the sweet spots, helping the Neftex data to synthesize data, and then based on that, we look to identify areas. And once we have identified the areas, then we go on, how can we plan our wells much better. Before I close, how do we look at improving the chances of success in Taiwan? One is doing our subsurface data gathering the best we can. The more the data, the better it is. Second, prepare conceptual models. These conceptual models are based on analog data and other things. Then we do our screening. Once we have these models are continuously updated as we drill new wells. And finding the heat and well targeting. As I close, what does Halliburton brings to the table? We've got Neftex, we've got Landmark, we've got the execution teams to execute these wells and also help to improve our modeling and the chance of success. As I close, this is what you can see, and this collaboration of data is quite an important aspect of how we do our sweet spot selection. Thank you for your time and appreciate you all for listening. Thank you very much.
Morning, everyone. So thanks for showing up. I appreciate the audience here today. It's really great to be here. It's my first time in Taiwan. My name is Brian Coates. As I was introduced, I'm the Geothermal Product Line Manager at Halliburton. And today I just want to talk to you about the artificial lift portfolio, how we use it, where we use it, and why we use it. So just to go through, here's the topics we're going to present. So like I said, we're going to go through a little bit of a primer on just what ESPs are. So for those that aren't familiar, we just want to give you a quick 101, what the major components are, how they work, and why they're there. Next, how they're used in geothermal. It's pretty important. That's why we're here. You need to produce the water some way. Some wells naturally flow, AGS wells like that, you might not need artificial lift. I'll put it out there right now. Not every well needs ESPs, but when you need them, they're very important. We're going to talk through some real-world performance issues, some challenges we've faced, kind of how we've gone through them, things like that, and then optimization strategies. So here's the ESP itself. So I'm going to start at the bottom. I know the writing's a little tiny, so I apologize for those in the back, but starting at the bottom, there's 6 or 7 major components that are involved in every ESP system. The bottom one is probably the only optional one, given the fact that there's so many other instruments out there. So the bottom one is your sensor, and that's what will give you motor temperatures, it'll give you intake pressures, it'll give you intake temperatures, vibrations, things like that. The problem with them is the electronics don't last that long. We're talking these things run 24/7, 365 days a year, hopefully for years at a time. Given that, the electronics just don't last that long in these high temperatures. So we have other gauges, completions teams, that's the optional part. Up above that is the motor. That's your workhorse, that's the engine of the entire system. That's where the electricity comes down, and that's where it starts. So there's two main types of motors. There's the tried and true squirrel cage induction motor. They've been out there for 100 years since CSPs were first installed. Chances are you've run induction motors just about anywhere. The new kind is a permanent magnet motor. So those are higher efficiency, higher power factor, and when we're talking geothermal, with parasitic loads are very, very important. You want to get that efficiency out of it. This gets you your extra 10-15% efficiency out of that. Above the motor is the seal. So that's probably the underappreciated component in the whole system. It's got a lot of work, a lot of jobs it's got to do. The first job, the main job, is the isolation, we call it. So it's got to separate wellbore fluid from internal lubricating oil that's inside of the motor. So we need to lubricate, we need to keep things nice and smooth running, but we don't want any of that well fluid getting into those electrical components where we can cause short. So isolation is number one. Equalization is number two. We don't want to create high pressure anything. We want to keep all our seals low pressure, makes things easy. So what it does is it equalizes the entire internal system for basically the same pressure as the internal wellbore, or external wellbore, I should say. The easy one is transmission. It takes the shaft torque from the motor, transmits it through the seal into the pump, makes things go. And then it's redundancy is the other thing. So when we're talking isolation, we want to keep that wellbore fluid as long as possible. So what it is a number of chambers, call it 18 inches, a number of chambers where it creates a tortuous path where if well fluid gets past this one, there's another redundant chamber underneath. So redundancy, 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 sometimes 4 or 6 chambers. Above the seal is the intake. It's got the simplest job out there, sometimes the most difficult, but all it does is take fluid from the annulus, puts it into the pump. And then lastly is the pump. So these are multi-stage centrifugal pumps. So you have an impeller and a diffuser. Rotating impeller, stationary diffuser. Takes the fluid, puts it into the diffuser, redirects it into the next stage. So every stage is rated for so much head or so much lift and then so much flow. And you stack, call it 20 stages together, it's going to create that same flow of those 20 stages, it's just going to be 20 times the lift. So that's how the main system works. From there, you can't really see it, but there's a long extension cord. It's just like the extension cord on your monitor, your computer, anything like that. It goes from your power source, plugs into the motor. And then on surface, it can look like a variety of things. Essentially, it's your power source. It's your light dimmer in the simplest sense. It turns the motor up, turns the motor down. But these days, it comes with a lot of advanced algorithms, control systems, power optimizations, things like that. And then on the right here, it's just kind of some things whenever you talk about geothermal artificial lift wells, these are the things that we have to deal with. So we're going to talk a little bit more about a few of them here. High temperatures, high flow rates, high horsepowers, kind of goes hand in hand with geothermal. On top of that, we've talked yesterday a little bit about just the aggressive chemistry. Sam mentioned it in his. And then most important, like I said, these things got to run for years, so reliability and run life are vastly important. So why do you use an ESP in a geothermal well? Well, they got a high flow capacity. So depending on the diameter of the pump, you can get upwards over 100,000 barrels a day, 20,000 cubes a day, anything like that. It's large volumes. The benefit is they also lift from very deep wells. We can go 1,000, 2,000, 3,000 meters of lift, no problem. They still run efficiently. So the pumps themselves these days are getting up over 80% efficiency. Motors with PMMs, you're looking at 90 plus efficiency. It makes for a really efficient system, a really efficient way to lift fluid out of the ground. They're compact. So other than the surface equipment, other than that surface control box you need, there's really not much on surface. It's a wellhead and a control box. They don't take up much land. It makes for easy for pad development. One of the biggest benefits is, like I said before, they're not made for every well, but for these older wells, these marginal wells, wells that are kind of dying on flow rate, or you need a little extra oomph, that's where ESPs come in. They can put them in the ground and they can start drawing that well down that much better. So for marginal wells, it's kind of the bread and butter, conventional geothermal systems, and then some GPGS. And finally, this is kind of been a recent development in the last few years, but when paired with remote monitoring, with data science, with all the AI that we've been working with, they really allow for adaptive tuning. So we can really crank out the efficiencies and lower that parasitic load that's required to run them. So I said I'd talk about a few challenges. So I got 3 challenges that I just want to go through a little more in detail. Challenge number 1, kind of obvious, high temperatures. Reservoirs these days that we're going into reach 240, 250 C. Typically what we're going in is the 160, 170, but as we develop, as we increase our technology, then we're going to push ourselves to the 250 C. When we get to that 250, that's where we start to see equipment problems. So you've got your electrical equipment problems where insulation degrades, so your insulation values go down, you have high voltage, you want to make sure your spark gaps are right. Your bearings start to wear faster, your oil has to stay in that nice lubricating viscosity, and if it's not there, then your bearings start to wear, you create vibration, it's a failure. So those elevated temperatures, again, they reduce the oil viscosity. Elevated temperatures also come with the risk of steam flashing. So if we're put in a well where the pressure is low, if we start flashing, it creates a problem for the pump lowers efficiency, and stop pumping. And then from a mechanical point of view, it's I think Sam mentioned in his, you're going down you're building stuff at room temperatures, you're putting a bunch of dissimilar metals together, they all grow at different rates, and they got to be able to operate at those high temperatures. So it's the ability, the mechanical stresses that you're putting on everything, again, running for years at a time. Number 2 is the chemistry. We've talked a lot about chemistry in the last few days. Geothermal brine is really hard on all sorts of equipment, metals. Also contains a lot of dissolved solids. Solids are hard on bearings, hard on wear. The corrosion, we run into a lot of problems with corrosion. When we talk about using exotic materials like Inconel, stainless, titanium in some cases. So one of the bigger ones we run into is scale deposition. So again, your high temperatures, you're in a big casing, and then all of a sudden it hits this motor, the pressure starts to drop. So when pressure drops, temperature increases, you start to drop scale in, and that's where we run into intake failures. We run into plugged pumps. The scales start to deposit on the motors themselves and almost create like an insulating blanket. So all in all, it just cascades into more and more of a problem. Some wells, H2S, CO2, just again leads to corrosion. So. Number 3, kind of goes without saying again, reliability and runtime. We got to run forever. That's our goal, is these wells last 20, 30 years. We want to be able to run as long as possible in order for you guys to maximize your returns. So unscheduled pulls are costly. If you don't have an unexpected failure or a short run or something to that effect, it costs money, it lowers your ROI. Those high flow rates that we've talked about, they'll accelerate wear. So we've got a plan for that. Use different bearing materials, different coatings, different things like that. And then monitoring systems. Again, I'll go back to the data science. We use remote monitoring for everything. We change control algorithms, we optimize efficiency, everything. So I wanted to give a little quick case study on a real world problem that we solved recently in the last couple of years. So this goes back to the scale deposition. And we had a customer in Europe that had continual intake shaft failures. Almost like clockwork, every 8, 9, 10 months, it would fail with an intake shaft failure. So after looking at what the problem is, doing some root cause analysis, we came up with a new solution, and that was a new intake. So what we did was, basically, we increased the size of the intake. The slower that fluid comes in, the less the pressure drop, which means less scale deposition, which means less scale, less failure rate. And then we looked at some other traditional, non-traditional methods, like using coated parts, using non-stick coated stainless parts, And then on top of that, we did some proactive scale mitigation, which goes back to the data science part of it. If you're monitoring these, you can start to see where trends happen, and all of a sudden your flow might drop a little bit, and you're like, that's weird. So then you can start doing the science behind it, saying maybe I need to shut it down, do an acid job, or do some kind of chemical treatment. So ultimately, the results is we tripled runtime. So the last system's still running at 3+ years, so we're still doing good in that part. The nice part is we reduced power costs at the same time. So allowing that larger intake area and that smaller pressure drop, that pumped enough to work as hard. So we reduced power costs, actually 15% in this well. So it was a huge, huge difference. So here's just an overarching key lessons we've learned over time. So the key is to adapt the ESP designs for the geothermal conditions. And that's, Sam's alluded to this, there's geothermal conditions are different everywhere. So we really want to know what the chemistry is, how the well works, pressures, temperatures, things like that. Number 2 and 3 kind of go together, but the grand theme is we have to be able to adapt quickly, make quick changes, and it's all about continuous development. We know not everything is going to go right all the time, but we're able to quickly iterate and get new designs out there in order to increase runtime. We're going to go back to the real-time monitoring. It's been a godsend in our ability to figure out how things are working, why they're doing what they're doing, and the science behind it. And then a system level alignment of fluid, chemistry, kind of goes back to the first one. Pump architecture, we need a whole system view in order to do this. So future improvements, again, going back to the continuous iterations. We're always looking to update, always looking to make things better. So right now, ESPs, you're capped at about 2,100 horsepower for us. And then that's at about 170 degree bottom hole temperature. We also have ESPs that are good for 250 C bottom hole temperature, but they're horsepower limited. So you're only looking at like 300, 400, 500 horsepower. So we're looking to bridge that gap and bring that 2,100 horse to 250. We're using advanced materials. Like I said, we're using Inconel, titanium, things like that. The advanced sensors. So like I said, our sensors have a hard time in these hotter well environments, but there are lots of completions tools. Fiber optics, there's vibration sensors, there's ERD gauges. There's lots of options out there that kind of give us this whole view of what's going on, not only with the ESP, but downhole, allowing us to make better decisions. And leading this all together integrates seamlessly with those surface, which makes for better control systems. So now we can autonomously control these ESPs for continuous deployment. I wanted to talk a little bit about Taiwan and how it fits into all this. And I don't want to rehash what everybody else has been talking about. It's an aggressive target to hit 1.2 gigawatts by 2030. I think it's possible. I think it's entirely possible. There are a few things we need to work on. So there are also a few advantages to well sites. So there's a number of wells that are already drilled. Maybe they're marginal. Maybe there's conventional geothermal down the pipeline or ESPs. So they're nice. They're compact. They're easy to use, and they run well. They can commercially support other lower marginal wells. And just to wrap things up here, so ESPs for geothermal. So they are a very powerful limit solution. They're not for everything, but they're very powerful when used. There are some key challenges that we've run into in the past. We've addressed them, and we will continue to address them with innovative designs, with system-level approaches, with this holistic view, kind of unlocking the potential with challenging wells. And we do believe it's a strategic opportunity for Taiwan. So, with that, I'm Brian Coates. I stick out like a sore thumb, so you can find me if you have any questions. Thank you very much.
Good morning, everybody. Thank you for the introduction. My name is Ken Kihara from Baker Hughes Climate Technology Solutions team, and I'm here with my colleague, William Tam. So I know it's a compact session, 20 minutes, but for the first half, I'll talk about who we are, Baker Hughes, because some of the audience may not know of what we do in the geothermal space, and my colleague William Tan's going to talk about specifically what we do on the surface solutions in geothermal. If we go to the next slide. Yes, so my colleagues on the other breakout sessions are talking about subsurface technologies, such as some of you may know that we are heavily involved in drilling technologies, such as drill bits, completions, ESPs. For this session, we're going to talk about surface solutions, specifically focusing on power generation technologies. Before we get into that, I just wanted to touch on who we are. So maybe for those of you who heard Baker Hughes, knows us as we're Houston headquartered drilling services technology provider. So here is just the organization chart that shows who we are today. So if we split our organization into half, the left-hand side shows OFSE, or Oilfield Services Equipment, which focuses on specifically subsurface. So, well constructions, oil field optimization, new energy. So these extend not only geothermal, but also some areas like CCS, carbon capture and sequestration. So this is the legacy Baker Hughes on the left-hand side you see in this chart. The right-hand side shows our surface solutions. So we break it into 5 business units. And here today we are from the Climate Technology Solutions, which heavily focus on not only geothermal, but you may hear things like hydrogen, ammonia, CCUS, clean power, these kind of decarbonization technologies that we also focus on. So again, we've split into 5, and like I verbally mentioned, our team here today in this room are from the Climate Technology Solutions. We heavily focus on CCUS, hydrogen, clean power. Clean power specifically means geothermal, which includes geothermal, such as steam turbines and also binary ORC turbo expander technologies. So my colleague William Tan will get into those details later on. This is just to show you some of the numbers from 2024, just to show the size of the company. We're about 28 billion US dollar revenue company. We heavily focus on also investments on new technologies, as you see on these numbers. And then company size-wise, we're about a little bit less than 60,000 numbers of employees globally. And we operate in more than 120 countries around the world. So talking about rotating equipment. So the surface technology comes from the legacy geo oil and gas, and we are headquartered in our headquarter manufacturing facility in Florence. So this is where we manufacture gas turbines, steam turbines, centrifugal compressor, reciprocating compressors, and this is where we've been heavily supporting the upstream oil and gas industries. So there's a high chance, even here in Taiwan, there's LNG imported. For the LNG upstream production facilities overseas, there's a high chance that one of our rotating equipment may have contributed in those projects for LNG. Here is just to show our various production and also testing facilities in Italy. So you may find 5 or 6 facilities, but again, our main manufacturing for turbo machinery and rotating equipment takes place in Florence in Italy. So this is our bird view of our facility in Florence. So this is about 35 hectare in plant area, and here is there's assembly, there's manufacturing, there's machining. So there's heavy machining assembly and also manufacturing taking place in Florence. Just some of the pictures that that they show you what we do in Florence. So this is just a picture of a gas turbine. This is not really relevant to geothermal, but this is a 100% hydrogen capable gas turbine. It's called Nova LT16. That also helps decarbonize the industry. Steam turbines, of course, we manufacture these for industrial, oil and gas purposes, and also geothermal, which my colleague William Tan's going to talk about. And also compressors. So again, as I mentioned earlier, we manufacture these centrifugal compressors, reciprocating compressors. And we do these kind of 3D impellers. So you know, our bread and butter has been really these you know, turbo machinery, aerodynamic, rotordynamics focused rotating equipment taking place in our headquarters facility in Florence. We also do testing capabilities. So as I mentioned, we've been heavily, you know, involved ourselves in the API oil and gas industry. So we do also string tests, which we basically use all the products that we, you know, are providing to the customer at our test facility before it gets shipped to the customer's site. So, you know, so this is a picture of gas turbine testing. This is also a mechanical running testing for API 617. And also we do high-speed balancing in these kind of, you know, vacuum chambers in our facility in Florence. And this is just a chart that shows, you know, our capabilities. So again, I mentioned rotating equipment, but that includes, you know, things like gas turbines, steam turbines, compressors. So these are just numbers that we have in our global install base. And I can comfortably say that our manufacturing capability goes around to 300 to 400 units per year. So you can, you know, roughly say we make, you know, one per day every year of these heavy-duty API designed equipment. And as you see, we have the onshore oil and gas upstream applications and also LNG. And again, I didn't mention anything about geothermal, which is a theme this week. With that, I'll just pass it over to my colleague, William Tan. He's going to talk about our geothermal surface rotating equipment capability.
Thank you, Ken. 大家好，我是来自马来西亚的William Tan， 我姓陈。So 在这个presentation 我会尽量还是用英文讲，但是有一些会穿插一些华语的，所以大家比较可能了解比较好一些。那刚才我的同事他有一些关于我们的公司的历史，其实我们已经加起来已经有超过接近300年的经验。因为我们是有地层下跟地表上的，就地表上，比如说在那个刚才意大利的佛罗伦萨，那个是起于1842年就开始运行了，所以那个已经有接近了，可能说接近200年的历史，所以我们在制造这些高科技的这些涡轮机这些，我们都是非常的有经验，当然现在我们是比较专注于这个再生能源嘛，就其中一个就是地热。Okay, so this is an overview of our geothermal surface solution. So not only we can supply for steam turbine, we can also have the binary ORC system, including, let's say, if you need to re-inject the NCG back to the reservoir well, then we also have the NCG re-injection compressor, and for this one we also have the extraction compressor. Yeah, if you will need to extract the NCG from the steam turbine. So on the surface, of course, we have the centrifugal pumps that to pump the brines or for the re-injection purpose, or even we also have the ESP on the subsurface. This is from our surface team. And when it comes to the whole system turnkey solution, for this part, we will always need the local partner to do that. Yeah. So for steam turbine, yeah, I just back to this one. Our capability for geothermal steam turbine, we can do from 5 to 80 megawatts. And for ORC, is from 5 to 65 megawatts. So, I mean, our range is in terms of in larger range. And this is the range that is always making the project more feasible. Yeah, we don't go for a smaller range like 1 to 2 megawatts. So this is a bit deep dive into our steam turbine. So as mentioned again, we can do from 5 to 80 megawatt for the steam turbines. So 这个就是我们的蒸汽涡轮机嘛，就是基本上我们可以做5到80 meg 哦，这个是一个蛮大的一个型号。And we can also do the steam for geothermal is from 4 to 30 bar. So this is also a good range that we can cover. And depending on the power, we can also do either single flow or double flow. 就是单流型或者是双流型的，就根据那个 power 的 requirement 嘛。然后我们其实，在意大利已经有相当多的经验，因为意大利的这个地热，它的那个brine 都是比较有那个硫酸性的，都比较高的。那么我们的这个材料都是会配合来就是跟它就是有足够经验去抵抗这样的硫酸性，哦。然后我们的这个 steam turbine 都是基本上都是这 reaction design， 这个是比较高效率的，比较高效率的。And for every steam turbine actually is a customized design because every geothermal field is had a different kind of steam condition, different kind of steam corrosivity. So of course we design our steam turbine with the blade that is compatible to that environment. And this is our typical scope of supply where we will provide the steam turbine with the loop oil systems together with our own generators, instrumentation, control panel, and sometimes we also can design and fabricate for the condenser. And depending on the project requirement, we can also provide the NCG extraction. And this is sometimes mostly required when we have very high content of NCG. Let's say it's 6 to 7%. So that's where our NCG extraction system come in. And of course, for every project, we'll send our people to the site for the erection and commissioning and supervision.
Who is the manufacturer of this steam turbine?
That is from Baker Hughes. Yeah.
Okay.
Yes, this is how my colleagues show the photos on our manufacturers' capabilities, right? Yeah. So this is our geothermal ORC solution. So we can do from 5 to 65 megawatt, and actually 65 is not our limit. We are still improving and expanding. So because our plant is really aiming for the big scale, and big scale is always the one that is making the project more feasible to our clients. And for our turbo expander or 那个膨胀机, this is a type of the actual expander. So it's actually quite similar to steam turbine. Yeah, so this is a way that can make it more efficient. Yeah, the design is making it more efficient. So for Baker Hughes, of course, for the whole ORC system, we can design it. Yeah, we can provide the engine design. We provide the main equipment, turbo expander, including our own generators. Yeah, and then, but for others, key equipment such as heat exchangers, the evaporator, the preheaters, the air cool condenser, there's a part that we can design, but we also will do the outsourcing, whichever that is competitive. And sometimes, even our EPC partner can do the selection if there is competitive. So we are quite flexible in that kind of scope. So depending on project level, also sometimes you can even provide the financing. Yeah, this is on a project basis.
And who is the manufacturer of this ORC? Also Baker Hughes?
Yes. Since our plant in Florence, we have like 35 hectares, and we keep on expanding. So these are all coming from our internal. Coming from internal.
From where?
From Florence, Italy. Yeah. So not only we are flexible in the scope of supply, we also flexible in the ORC design itself. So basically for our ORC, we can design, with a geothermal brine temperature from 130 up to even 230. So, since we have both the solution of steam turbine and ORC, so sometimes when it's like above 200 or maybe close to 200, we can even decide which ones can give you the best efficiency. Yeah. So because we have both the solution. So in terms of power, also we can give you either single pressure level, two pressure levels, whichever that can give the project more feasible. Yeah, because you will study not only on the efficiency, but we also will study on the capex. 就简单来说，这个我们就是很松动，就是除了我们的那些所提供的那些机器，我们的这个设计也是很松动，就是说有这个单压力的，有双压力的，就看这个怎样去配合，给你达到最好的这个效率。除了效率之外，我们也会考量那个你们所需要投进的资金嘛。Okay, when it comes to generator, yeah, this is not the manufacturer in Italy, but it's coming from Czech Republic. So back in 2022, Baker Hughes has acquired this generator company called Brush. So Brush actually has been very popular in geothermal application. And actually we have been supplying a lot of these generators to even our other competitors in the past. So, I mean, when it comes to geothermal field, you have to make sure that the materials of the generator have to be compatible with the environment. Because in geothermal field, you have 硫化酸，有这二氧化碳嘛，所以这些发电机它们的材料就可以配合这个厂商的这些气体，因为它比较有侵蚀性嘛，所以我们的这些generator 的材料都是基本上比较多倾向于不锈钢或者是铝，因为它比较能在这样情况下比较能耐比较久，没有跟这传统的generator的材料。So for these generators, we can build up to 200 megawatt. So this I would say is more than enough for any geothermal plant. And we understand that Taiwan is going very fast to reach your gigawatt kind of geothermal install power. So of course, the bigger the better. And then, yeah, we have enough capacity to help you to reach that goal. So we can do in either 2 poles, 4 poles, and Taiwan is a 50th country. So there's no issue. So yeah, this is all be manufactured in Czech Republic, 在捷克，这些发电机都是在捷克那边制造的。这就是我们的最后一个。如果说你们在这个 geothermal 的 plant， 你们有这些 NCG， 就是不凝结的气体，比如说二氧化碳或是硫化氢的话，如果你们要把它回注，这样我们就还有这个回注的压缩机，因为这些压力你们所需要的就是蛮高的，所以我们这个还有这些的方案。除了这个回注的压缩机，那么我们还有这个如果你要抽气排气的压缩机，我们都有。因为有时候你们有太多的那个 NCG 的话，那么它会造成那个系统的效率就比较低，所以你可能就需要考虑用这个NCG compressor。So 我们的 presenter 就大概在这里，谢谢大家。
So good morning, everybody. Thank you very much for being here and for devoting your time to my presentation. I'm Desiree, I'm Italian, and I'm sales manager for Far East and Southeast Asian market in Turboden sales department. Turboden is an Italian company that is one of the leading company in providing ORC power plants. For the purpose of this conference, of course, we will focus on the geothermal application. However, I would like to make a point on the fact that we are also covering other applications through ORC, like waste heat, biomass, and other applications. So wherever there is some heat that can be converted into electricity, we will try to do that. Turboden is more than 40 years old. It was founded in the 80s in Italy, and it is based in Brescia, which is halfway between Milan and Verona. And in 2013, 51% of Turboden was acquired by Mitsubishi Heavy Industries. As of today, we have more than 450 power plants in the world, 50 countries, including Asia. Our mission is to provide unique, reliable, and advanced technologies founded on our core proprietary turbo machinery, with the aim of maximizing the value of renewable resources and energy efficiency, and accelerate the transition toward power by low carbon technology. The power plant that you see in the picture is the geothermal power plant in Germany. So as I already mentioned, we have global and proven experience. We cover 50 countries, 460 power plants to be precise. And the biggest one that we have, you can see at the bottom corner on the left, is 29 megawatt electric. It's a geothermal power plant for EDC, Energy Development Corporation in the Philippines, that was inaugurated in July 2024. However, the record was beaten. We contracted 120 megawatt electric, composed actually by 3 power plants, 40 megawatt each for Fervo Energy in the US. Well, MHI is a much bigger company, as you know, and we belong to the energy division system. The guy on the left, is Professor Mario Gaia. He's the founder of Turboden company. He was professor at Politecnico of Milan, and together with his best students, he founded Turboden in the 80s. He's still very active in the company, wonderful person. In 1998, Turboden sold his first commercial biomass project, and in the 90s entered the geothermal market. From then on, the company grew a lot, not only in terms of figures, but also in terms of technology. Today, we have added other 2 products to our portfolio. We also are delivering and engineering large pump, as well as gas expanders. So why Turboden? Turboden is very highly experienced company in thermodynamic design. We cover from the design to manufacturing and after sales of our power plants, which are all highly customized based on the type of heat source that we need to recover from. So we design the heat exchangers. We choose the proper working fluid that maximizes the energy conversion from heat to power, and we do the after sales of our power plant. We also are able to integrate in existing processes, like we will see later. So here at a glance, you can see all the different parts that Turboden is covering in terms of engineering and scope of supply. This is in particular a 14 megawatt geothermal power plant that we have in New Mexico. So the good thing basically is also that they are often installed in very remote area, and remote control is a key to this kind of application. Our after sales department, which I like to mention because I often get the question, can you do after sales in Asia? Yes, we can. We do it. The after sales department is located in our headquarters in Brescia, in Italy. However, we have also 3 subsidiaries in the world and 3 international service companies that are partner for the after sales service. We can provide 24/7 assistance for troubleshooting and remote consultancy, as well our design software for remote monitoring. The after-sales services are also highly customized depending on the needs, on the location, or the type of application of the power plant. And this proudly leads us to a average availability larger than 95%, and a response time of remote service engineer below 2 hours. So we already heard a lot about conventional and non-conventional, but we want to mention that we already have experience in all of the applications of the binary system that you have heard yesterday and this morning. So in a traditional application, a full binary system is typically the most straightforward solution, meaning that the URC is recovering the 100% of the geothermal source that is coming from the ground. That means that The geothermal resource is separated into steam and brine, which are both conveyed to the ORC to produce electricity out of them. However, there are many traditional flash steam turbines in the world that are only using the steam portion. What the ORC can do is to use the brine that is dismissed by these former power plants to add other power, like we will see later. For unconventional or next-gen geothermal application, instead, we have the courtesy of images of Ivor and Fervo, which are both customers of Turboden. With Ivor, we are building a 8.2 megawatt electric ORC power plant in Germany. For Fervo, a 120 megawatt, which I already mentioned. The first 40 megawatt are planned to be started up next year. So here are a list of selected projects belonging either to full binary or flash plus binary or unconventional. These are power plants that we have in Germany. They're all ranging between 4 to 6 megawatt. In Germany, the geothermal source is only composed by brine. It's a kind of hot river running under the ground. So the ORC is only fed by brine. They are running on refrigerant mostly because of local requirements, and they are running dry solution. They do not want to use water for the cooling, so all the ORCs are equipped with ACC, which also had to be designed for very low noise emission. Kyushu Electric is instead a 6 megawatt power plant that we developed together with our mother company MHI in Japan. That one is fed by brine and steam. And then we have other in Germany, in Croatia as well, 17.5 megawatt, 14 megawatt in the US, which we saw the picture before, and other in Germany. And then we have here the power plant for Energy Development Corporation, for which I have a bigger picture to show you. So this is the power plant that we have provided, and that one at the top is the flash power plant. So we are taking the brine that the other one is not using to add another 29 megawatt, while the original one is 140. So total almost 170 megawatt electric. Another combined, let's say, bottoming application that we have instead is in El Salvador, where we are adding another 8 megawatt to an existing flash turbine. And we have already mentioned the collaboration with Ivor and with Fervo. And last but not least, we are going hopefully soon to start up a 5 megawatt power plant for CPC. It's a geothermal application, of course, that suffer from two or three typhoons. Therefore, a slight delay. We hope everything will go smooth this summer. This is not the only one that we have in Taiwan. We also have a 10 megawatt ORC, but that's not for geothermal application. That is a waste heat recovery from an existing industrial process. So here is general presentation of what we do. Our experience in ORC is well known, and we really hope we will have soon other results in Taiwan. We very much believe in the potential of the countries, and we are eager to expand our collaboration. Thank you very much for your time.
Very much, Claire. Kia ora everyone. As Claire mentioned, I'm Dr. John O'Sullivan. I'm the co-director of the Geothermal Institute at the University of Auckland in New Zealand, and it's a real pleasure to be here today to talk about advanced modelling for resource assessment during the exploration stage. At the stage that we are here in Taiwan, when we're looking at developing new resources, a key part of that is trying to understand, what is the scale, what's the style of the development that we're going to be proposing, what kind of return on investment would you expect? And one of the important things is understanding maybe some of what is the worst case, what are the failure modes, what should we be looking out for when we're trying to develop these geothermal systems. And we need to make these decisions using our best evidence, not just guessing. And we have some industry standard tools that I'll talk about as well that I've been using for a long time. But what I'm going to show you today is how we use uncertainty quantification with advanced reservoir modeling to give us better evidence for making these decisions. And this is pretty new technology. I'll talk this through. We first presented this in 2022 at Stanford Geothermal Workshop. And I'll talk through the projects, but we've applied this successfully to a number of commercial and research projects now. And one of the reasons that we can do this is we now have the capability of running reservoir models in the cloud. We've been partnering with AWS and Microsoft Azure, but particularly AWS. And, Taiwan is a very technically advanced society, and so you'd be very familiar with this, but the web-based, cloud-based computing services mean that we can run ensembles of reservoir models very quickly and very cheaply without needing a lot of expensive IT equipment in every company. And so just as a quick comparison, a standard production scale reservoir model that used to take 8 hours to run on existing technology developed at Berkeley and at the University of Auckland now runs in about 3 minutes and costs less than $1 to run. So this is an absolute game changer, and you can run 10,000 models for $1 each, all at the same time, and get the results back in 3 minutes. And that is an absolute game changer for how we think about it. This is something that oil and gas have had access to this technology for longer, and so this won't be unfamiliar to people coming from oil and gas, but for geothermal this is brand new technology and really is going to change the way we do our decision making. And these are just some examples of, these are projects in South America and in New Zealand and in Indonesia, where again we're just looking at orders of magnitudes faster, 12 hours to 17 minutes for these large scale models. And the key thing, one of the things that we thought when we developed this new technology was that we would run higher and higher fidelity models. And that is, we have been doing some of that, but what we found, in fact, the real value wasn't being able to build very detailed, very complicated models. The value was being able to run standard models very quickly. So being able to run 10,000 realistic versions of a geothermal system and seeing how all of those 10,000 perform, which ones fit the data we have the best, has been a real game changer. And so that ability, uncertainty quantification gives us, it means that we can produce forecasts that give a range of options, and that's key for making robust decisions. Instead of saying we're going to produce 20 megawatts, we can say, the P90 is that we are going to make 15, and that is a much better estimate for the decision makers. So the ability to set up models that are consistent with the geological conceptual models quickly, run them very quickly with our open source simulator YWERA, and then using uncertainty quantification mathematical tools, that's what gives us the ability to do this. So our approach at the moment is we still go through standard calibration techniques to get us in the ballpark of what we think how the geothermal system is behaving, and then we'll generate thousands of models by applying ranges to all of the parameters in the geothermal system. So we have, if you can build a geological model for well targeting, we can build a numerical model from that and then test out realistic ranges on all of those parameters that make up that model. And so what happens is once you put in ranges of parameters, and you can see some of these, for those, this is going to get a bit technical, sorry, but we're looking at permeability ranges of 2 orders of magnitude easily in these. So you can look at very broad ranges of possible heterogeneity in the system. And you can see then we run those models forward, and all of them generate some representation of a geothermal system. And what you can see, this is from an example problem where we have a number of wells. This is a map looking down. Those are some structures, faults. And you can see every grey line is a different geothermal model. And so there's we're like 200 degrees variation across these different models. And the dots show the measured data from this system. So you can see by creating a big range of input parameters to these reservoir models, we get a big range of possible representations of the geothermal system. And then what we do is we use that data and the uncertainty on the data, which is really key. We're not just using the data, but the uncertainty on the data to tell us, well, which one of these thousands and thousands of models are a reasonable representation of the geothermal system. And that's what, in this case, and those are parameters you can set. You can say, how much do I trust different types of data? Here we're using downhole temperature, but the key thing with this method is we can use any data. So, we're talking to Berkeley about how we can use the seismic data as well, and to constrain this. We're already using resistivity to constrain this. It doesn't have to be, it can be any type of data at all. And then once you take the models that are the best representation of the true system, you can run through and you can do forecasts. And I just showed this in the production reinjection workshop. But you can do forecasts forward, and now you get those really important ranges on your forecast, saying this is our expected P50, but this is the worst case scenario, this is the best case scenario, given the range of possibilities. And this is the interesting case showing without drilling new wells or with drilling new wells, and you see what you would expect to see, that the uncertainty goes up when you're adding new wells to a system. So given that we've got this new ability to do uncertainty quantification using advanced modeling techniques, let's think about geothermal resource assessment. So the traditional method, which is older than I am, I turned 50 last year, this is over 50 years old, is a stored heat calculation or a heat in place calculation. It's a very simple method to calculate the energy that can be extracted. It's the kind of thing that I teach my first year master's students how to do this and answer this in their test problems. So we do Monte Carlo over a very limited number of parameters. And the important thing is we have something called the recovery factor. Now, the recovery factor takes into account hundreds of different things, and it can be, how deep you drill your wells, what's going to happen to the recharge of the system, what type of wells you're drilling. All of those factors have to go into the recovery factor. It's very uncertain. No one knows what it should be because it's a fudge factor or a factor that takes into account so many different variables. This is fine as a first estimate, a rough first estimate, but we can do much better than this. This is 50-year-old technology. So the idea is that now that we can run reservoir models so quickly that we can run thousands of them, what we can do this at the very earliest stage. As soon as you can draw a conceptual model or build a geological model for drill targeting, we can run reservoir models of it, and we can run thousands of them. And we can test all of them and see which ones match the data. And the key point is, for a resource assessment for a greenfield system, we do uncertainty quantification, but we just have no production history data. So we're only using that early stage exploration data. But the important part about it is we're forecasting forward using models that respect all of the reservoir physics and the wellbore physics. And I'll talk about it and I'm putting an example of that too. So this is it. This is the new method. It's basically fast. We set up models very quickly, we run them very quickly, and we use some clever mathematical tools to choose which models fit the data we have the best. and that gives us uncertainty quantification. And what we're going to do is we're only going to use exploration data, and that gives us a method for resource assessment. So what does that, this is the example I just mentioned. We use the resistivity to infer a clay cap, and then we can choose all of the models which match the clay cap to some degree. This is obviously for a volcanic or high temperature system, but as I mentioned, we're going to work with all different types of data, seismicity, chemistry. We can use any data to choose the models. So this is a temperature plume, and so we expect to see clay forming at around 190 to 200 degrees. So we know that we should only choose geothermal models that produce temperature distributions that align with that. And in this case, we don't have any downhole data because no wells have been drilled, but you can see the same thing happens when this was all of the thousands of models. When we look at the ones that fit the clay cap, we end up with a much narrower band of models that we select going forward. And as I said, this can be any early drilling, so maybe you've got 1 or 2 wells. It can be geothermometers, we can do flows to surface features. We're looking at chemistry, and we're going to look at seismicity to bring into this too. And then what we do is we have an algorithm which is pretty simple that basically stress tests every single model. All of these red models, we then stress test them, seeing how much fluid or energy can we pull out of the system with realistic production and reinjection. And so that we loop around in an iterative way, adding more production and reinjection until we see a maximum amount of energy being taken from each of these thousands of versions of the system. And again, that only works because we can do this so fast, right? So we're running a forecast from a reservoir model that might have used to take 2-3 hours. We're doing it in 30 seconds. So we can do it iteratively, and we can do it on 10,000 computers in the cloud. So we've already done this on many systems in Indonesia, and which we've published at some conference papers, and there's going to be a journal paper out soon. And we're actively working with the Renewable Energy Ministry in Indonesia to look at using this method in a way to support their database of greenfield systems as a systematic way of providing realistic, robust estimates to the public. We've also done it in other locations as well, and that's in Colombia and also in Portugal. So this is the kind of results that you get out of those estimates. This one, the comparisons with the stored heat were fairly similar, and you can see, so each of these grey lines are forecasts, and we look at you can get the P90s, P10s for the total amount of power out. And so, as I said, every single one of those is a full-scale geothermal model run through to forecasting, including wellbore modelling for the production and reinjection. And just before I move on from that and finish, one of the things with the wellbore modelling we found, it was this, in this case, the stored heat gave pretty similar estimates to the simulation-based resource assessment. But one of the other projects we did, the results were very different. And that was because in the system we looked at, it was actually under-pressured because of a very deep water table. Now, there's no way to account for that in a stored heat calculation except by setting a very low recovery factor, which there's no reason to do if you weren't aware of that wellbore physics. And what we saw with this new simulation-based resource assessment was that we got a much more realistic estimate of what the resource availability was. So the key thing about this is we're not using necessarily more information than a stored heat calculation. We're just using it better and smarter and making sure that we're obeying the laws of reservoir physics. You know, we're looking at how the fluid actually flows and how the well bores perform as well. And now, as we expand on the data that we're going to be using, then we are going to be adding extra information into that. And you have the possibility of using a whole range of exploration data like being gathered here in Taiwan to essentially help build more robust estimates and de-risk development by having a more accurate representation of the resource. And so it's only possible this is only new technology because of those advancements in being able to do reservoir simulations so quickly and so powerfully using cloud-based technology. And we now have several of our long-term clients and collaborators. These are key deliverables. So all of our new projects, we always offer this as a deliverable, and in our relationship with Contact Energy in New Zealand, and also clients in Indonesia and Australia, we deliver quarterly forecasts with uncertainty quantification included. So this is a standard deliverable. There's no reason not to do it. The technology is now available, and the value the value of having these robust forecasts is not to be underestimated. Thank you very much. Any questions?
완전히 기회가 어쩌저리 원해 교신. But I'm going to speak in English today. I've been studying Mandarin for 3 years and nobody understands me. Anyway, we've been working here in Taiwan for 5 years now, and we've been assessing, I don't know how you express it, but raw, open field potential geothermal sites. In other words, no intervention, there's been no wells, there's been no EM, there's been nothing. So what are we using to get an assessment of potential for geothermal development? So this is me, of course, and then my partners are in the U.S. We have a partnership with them. You'll hear about their instrumentation. We have a partnership with Professor Li Xiaoxing here, and his team, all here, and then our new student here, G.E., is starting a PhD on this topic. So we're very pleased, and we're making inroads into influencing geothermal development in Taiwan. I'm going to talk about tomography and rock physics. First, I'll talk about tomography. Tomography is our basic source of information. What we want to understand the subsurface. If you think about it, very few technologies are telling you what's going on beneath the surface. You have geology, you have springs, you have geochemistry, but very few technologies are telling you what's going on beneath the surface. You have EM, and you'll see some differences with that. So we feel we have a technology that we've been working on developing for years that can give us valuable information from the beginning to the end, because it also can monitor reservoirs. But so what is tomography? Well, we have instruments at the surface of an area of interest. Usually this is something like 5 by 5, but it could be 10 by 10, but you have to add more instruments, because to get high resolution, we want an instrument recording about every kilometer or less. What are we recording? Little earthquakes that are occurring at depth. So this is the energy comes up through your volume. It gets modified by the conditions of the volume, the water, the permeability, the fracture zones, the consistency of the rock. So all this energy that leaves in a little earthquake comes up and recorded at the instruments. Of course, you don't do it from one earthquake. We need typically 300 at least little earthquakes, by the way. And they occur quite frequently. In Taiwan, we can get a lot of earthquakes in a very short amount of time. Even in the U.S., I'm not sure anybody here from Nevada, but over California, we have plenty of earthquakes in California, but in Nevada, surprisingly enough, we have very few small earthquakes. But, they occur there too. So just to get you started here, this is typical tomography result of a resource in the detail. And this is the same resource assessed with EM. So EM it does identify the same conditions, but much less resolution. But not only do we get more resolution, as you're going to see, we get a lot more information. This might tell you about fluids, but we'll tell you about the fractures, about the permeability, about the chemistry. So here is a typical void with earthquakes occurring in it. Something like this is 10 kilometers, in this case 5 by 10. So we developed an end-to-end solution for rapid, inexpensive exploration, modeling, monitoring, and providing drilling targets for reservoirs and active seismic areas. I was going to say in Nevada, they said, well, there's no earthquakes in Nevada. Well, when you put in our instruments in, you find out there are earthquakes there. But let's talk about rock physics. When you record these earthquakes, you do the tomography, you get an image of what's going on in the depth. How do you interpret that? Well, we interpret that with rock physics. It turns out with recording the VP and the VS, which is the P wave and S wave travel times, and the QP and QS, which is the attenuation properties, those four pieces of information can be manipulated with mathematics to provide several elastic parameters of rocks. These are typical elastic parameters that are mathematically, physically derived of what rock behavior can be. For example, Poisson's ratio, bulk modulus, shear modulus, lambda. You'll see all these in your physics classes when you derive the wave propagation in a medium. You'll see all these parameters. And so we derive these parameters, and each one of them tells you something else, something different about the geology. It'll tell you, for example, high shear modulus, very often that's usually the case of a very weak zone. But shear modulus doesn't see water, so it will tell you about the geology excluding the water. Whereas bulk modulus will tell you something about the water. So you can have a highly fractured, highly permeable zone and have a very low shear modulus, but a very high bulk modulus because it's full of water. This would not see the water, it would only see the geology. So every one of these tells you something different about your geology that you're looking at. Okay, so where are we going from there? Oh, here's the kind of things we try to get out of our information. We get cracks, fractures, and faults just from the locations of these earthquakes. I'll talk about that later. We get moment tensors, which is identifying how the earthquakes rupture. So you might find a zone where you can see ruptures of a certain type. For example, normal faulting is more common to propagate fluids from depth to the surface. Steam, we can identify steam by Poisson's ratio. One of our elastic parameters can identify what is steam and what is water. You'll see an example of that later. Like I said, for bulk modulus, you can identify fluids by Poisson's ratio as well. And if you look at all of these, plus your other pieces of information you might get from other sources, we can identify the porosity, the permeability, and the saturation of the volume. So these are all things you can get of your volume that you may not see at the surface. Keep track of my target, 5 more minutes. I just want to point out that the surface very often is not what's really going on. And where we are in California, our geothermal wells, you'll see some examples of that, are 25 kilometers from the surface hot springs. We see hot springs everywhere, and they make hot spring spas, and nothing where we have the actual geothermal resource, because Mother Nature does not always obey properly. You don't go to a hot spring at the surface and drill straight down and find a geothermal resource. Often. In fact, in Taiwan, we find these surface wells, 1,000 meters or less, are tapping into rainwater, leaking into the surface, and getting hot springs 40, 50, 80, 90 C, but the actual real geothermal sources are down 2 and 3 kilometers, not even connected. So if you're going to take a hot spring and start drilling straight down into a hot spring, you may be happy for 10, 20 kilowatts, but you're not going to get 40, 50 megawatts out of that. Okay, am I going to run out of time? I've got to keep moving here. So this is what we're doing with rock physics. We're trying to, a lot of these rock physics parameters are developed in the oil industry. There's very little of this was done in geothermal. But we got the idea that, well, all this research in the oil industry, we could apply some of that to geothermal. They've been doing this for decades. Rock physics is a primary degree of study for anybody going to work in the oil industry. But and what they found are things like this. If you look at Poisson's ratio down here, you look down here, different values of Poisson's ratio. tell you different things about the water. And this is, we really got this from oil and gas, but we're trying to apply it to geothermal. For example, very low Poisson ratio can indicate steam. Very high can indicate water. Mostly in the middle is normal material. No water, no steam, just part of your normal geology. In field instrumentation, we built our own instruments. We found them to be very inexpensive. We can develop a lot of these in a very inexpensive manner. And they have all these kind of attributes, which really, my partner, I told you at the beginning, is the genius in electronics. He's really better than what's commercially available, but we keep this for our own use, that they're very valuable. And they record the little small earthquakes. We have students here in Taiwan work with. You can guess which ones are from the U.S., these two here, but the Taiwan students, and the instrumentation is easy to install, quick, and they record these very, very sensitive, very small earthquakes. Like I said, in Nevada, they were saying there's no earthquakes. How can you do what you're doing in Nevada? Well, you put these out there, and they are earthquakes. They just didn't feel them. They just didn't have small, sensitive instruments to record them. I'm not doing it for time. I talk too much, I know. And we build, like I said, we give a shout out to Jerry here. He's here. Just got married a week ago. Congratulations, Jerry. And we build them ourselves here in the lab at Professor Lee's lab. So we just crank them out because we have 200 or 300 of these. And that's a massive amount of data processing, which we've also automated and which we can process pretty quickly now. It's all a step. So let's look at Taiwan. We've been here in Taiwan now for 5 years looking at some of these different geothermal resources. I'm going to talk about this up here. Very interesting area up here, which is a volcanic area. Most of this is accretionary prism, and here is mostly volcanic, but it's also hot up there because of the volcanoes. So here's one of our results, in a tomography result, for a volume that's about 5 by 5 kilometers in area, and then 5 kilometers, so it's a big cube of the Earth of interest. And this is what you might call normal values here. This is Poisson's ratio. Normal will have two big cavities, A and B, but the rest of it is kind of like normal, your normal geology. So, okay, fine. So what happens with A and B? Well, it turns out B fills up with steam. It's a very low Poisson's ratio. And A fills up with water. So we have a water reservoir and a steam reservoir right next. They turn out they're right along a fault here, which is the source. But here it gets us closer to the volcanic heat, and it's turning it into steam. Down here, it's water. But either one is a good reservoir because they're both hot. Depends on what you want to do. Here, if you isolate them, here's your two reservoirs. There's some wells that have been drilled in there to validate what we've seen. And so you have the steam reservoir as B, and the water reservoir is A. Here's the detail of your reservoir. So here we can provide you with a drilling target. If you were going to drill here, make some plans of what you were going to do. All right, now I'm going to go back to California, the geysers. Just to point out that this is San Francisco. Berkeley is over here. Up here is the geysers. It's an hour and a half drive. It's our outdoor living lab. We go there all the time to do experiments, to get information that we can test. Here's a test we did here with a dense network of recording stations over 5 by 5 kilometer area. And we're looking at these wells here. There's 4 wells. So this is a case where we already know what's there. This is where we validate and test our theories. We already, in cases where we know what's there. So here is wells here drilled into this. This is Greywacky. It's 260 degrees up here. It's 400 C down here. 260 up here. And then it cools up in here. But this is all Greywacky. Volcanic heat source down in here. It gets really hot, really hot. So what do we do with this? Well, we look at water injected in these wells. So there's water being injected in these wells. And what we found is that it creates little earthquakes. When you put cold water into 200 or 400 C temperature geology, you get a lot of little earthquakes. And here they are coming out of the well. And here's what the water does. The water has altered this this valley, which is mostly normal geology up here, with steam. A lot of it's steam. It's very hot. But here is where water has saturated it. So we can see when you inject it, we can see what water has done to this. The point is here, we did our tomography, we located the earthquake, we identified an anomaly, and it fits exactly below the well where water was injected. So we gave you the confidence that we see, what we see is real. We know that they put water in. We know that at the bottom of the well, we see the effects of it would be theoretically what water would do, and we see it. Over here, we see nothing because they didn't do anything. They haven't started injecting water here yet. This is a dry well, pristine well, drilled into very hot material, so nothing happened. And here's the two other cases. But here, they started injecting in here right away. We saw the earthquakes, and we see the water at the bottom of the well. More validation of what we're doing. But I want to point out, this was a failed experiment because they drilled two wells, actually. The well over here, and the idea was to put water down this well. It would induce fracturing and get a flow of the water to the second well, and they would get an engineered geothermal system. Big mistake. You don't drill the second well until you know where the water is going or where the fractures went. And so here, for example, you might have done better to drill the second well over here instead of over here. But they've learned now, and Forge, our second developed area, they're now putting the well in later, not at the beginning, hoping to reach it with fracking. But if you do hydrofracking, you can see where your fractures went. When you start injecting water, you can see where your water went. Then you can drill your second well with an enhanced geothermal system. I know I'm running out of time, so I'm done with that. I'm going to go on to, I'm just going to skip that. I know I'm running out of time. Go to Taiwan, and I'm going to go to the Philippines. Okay. In the Philippines, they already have a geothermal system, well developed. So here's but we did the tomography because there they want to do reservoir management, not reservoir exploration. So here's the volume of their area. Here's the cap rock we identified. Here's their wells. Here's the heat source below it, and here's the reservoir in here. So there's some questions to be asked. Like in our case was, can we expand the reservoir as it is, which is over here, to north of this fault here? There's a fault here. The question was, can we expand the field over to here? We said no, because over here, look at this. This is QS, and she's written a paper about this. It's very indicative of water, like they have in their reservoir. Very good resource of water in a hot reservoir. Over here is a fault, and over here is QS is very high. It flips exactly over that fault. It flips from very low to very high. Well, very high is dry. Very low is wet. Oh, I got 5 more minutes. I thought we only had 20 minutes. Okay, good. It flipped over along this fault. Our tomography, in other words, is so detailed, so such good resolution that across the fault we can see a flip over from a very saturated area to a very dry area. Well, unfortunately, they didn't believe us at first, and they drilled anyway because they had other surface indications that they believed and found a dry well. They said, sorry, but then they've learned, and now are not expanding in that direction. That's the end of my talk. So I just say we've improved data collection and processing for reservoir monitoring. You can start with an area where you know nothing, and we talked to John O'Sullivan here about coordinating with his approach. We're putting some ground truth in what you know at depth with what he's modeled for all the different possibilities of reservoir models, and I think the two could go together well. Well, this is all the improvements in instrumentation and computer processing where we reduce the time. And so all this is reducing time to get the results. Because of that, we can get near real-time reservoir modeling. If you remember that well where they had not seen any effects of water, when they started injecting, immediately saw the effects of water. Well, if you're monitoring a reservoir or you're monitoring hydrofracking, you can see almost immediately where the water is going. You have a good vision of what's going on at depth. So for reservoir management, for identifying drilling targets, for assisting in hydrofracking engineered wells. You can monitor what you're doing and see it. And so the other point is that the micro earthquakes, the little earthquakes we record, can be used along with rock physics to apply some very detailed and important information for geothermal systems.
Thank you for introduction. First of all, I'd like to thank the organizers for giving me the opportunity to talk in this workshop. So today I'm going to talk on the SCRIT-TEM technology for geothermal exploration in both green and brown fields. And this is a picture of Kuju Mountain in Kyushu area in Japan. So there are many geothermal power plants around these volcanoes. Okay, this is outline of my talk. So after briefly introducing our company, SUSTEC, I'll talk about the SCRIT-TEM method, and then I move on to the geothermal exploration and show you some track records in green and brown fields and also in national park area. And finally, I'll talk about the observation with injected fluid and finally summarize it. Okay, SUSTEC was founded about 5 years ago by taking over the technologies developed over 20 years at a non-profit organization supported by the Japanese government. SUSTEC is located in Yokohama City, and we have collaboration relationship with Sumitomo Corporation and Techno Imaging. So Sumitomo Corporation is one of our shareholders and support sales and promotion. And Techno Imaging in the United States work on the 3D version of TEM data. And one of our core technologies is a high-temperature superconducting quantum interference device, HTS squid magnetic sensor with ultra-high sensitivity. And the other is a squid-based transient or time-domain electromagnetic system, SCRIT-TEM, and geophysical exploration services. And our targets are geothermal, mineral resources, and CCS IOR, EOR monitoring. Okay, the key features of HTS squid magnetic sensor is a lower field noise at low frequencies, less than 10 hertz, which is suitable for deep exploration. And another advantage of squid sensor is wide bandwidth in frequency with the flat response, which is also suitable for the AM data analysis. And HTS squid sensor using high temperature superconductors can be operated by using liquid nitrogen, which is low cost and available anywhere. So this sensor is suitable for field use. Okay, our sensor has a special thin film material structure. Owing to this structure, our sensor can be operated stably in the changing magnetic field. And the sensor is very, very small. It's a 50 millimeter square. Okay, now next is the exploration of a SCRIT method. And for the case of mineral exploration, we typically use a 100 to 200 meter square loop, and we apply pulse-like alternate current. And by measuring the secondary magnetic field generated by subsurface current and applying 1D version, we obtain the resistivity layer structure and expression depth. For conventional TEM, using an induction coil sensor is about 500 meter. And by using a squid magnetic sensor, the expression depth is extended to 1,000 meter. Okay, for the case of deeper targets, such as geothermal reservoir, we employ several kilometer long line source with both ends grounded, and which just change the position of the squid sensors. And we measure the XYZ magnetic field transient at typically 40 to 6 point. And applying 3D version, we obtain the 3D resistivity, subsurface resistivity structure. Then expression depth for such a configuration is over 3,000 meter. And recently, this expression depth reaches over 5,000 meter. I will talk about later. Okay, this is a picture of our recent SCRIT-TEM system named SUSTEM. Okay, the weight of the total system is only 20 kilograms, and one person can carry the whole system. So here, this is a sensor class. That here, the three sensors, SCRIT sensor is cooled with 0.7 liter liquid nitrogen. And we can continue to operate this for 70 hours, long enough for one-day exploration. And the noise level in TEM measurement is very small, about 1 picotesla level. Okay, in this table, we compare the features of a skid TEM with other electromagnetic methods, including MT, CSEM, and conventional TEM. And you can you can see by repeated measurement and stacking of averaging procedure, we can decrease the influence of environmental noises for CSEM and TEM. And there is no influence, moreover, there is no influence of primary field for TEM because we only take the data when the primary field is off for TEM case. And this enables measurement with the highest signal to noise ratio. And another advantage of TEM is signal intensity is proportional to the cube of the straight conductance. So it's this means this method is most sensitive to anomaly or variation of the conductance. Okay, now let me move on to the geothermal exploration. So we propose two ways of utilizing skid TEM method. And one is here the use of skid TEM to determine the drilling point precisely after the wide area exploration using MT, and to reduce the initial risk of development in the greenfield. And the other is the use of skid TEM in already developed areas, that is a brownfield, and to find additional drilling point to keep or enhance the power generation capacity. Okay, now I'd like to show you some of our track records. The first one is exploration in South Sumatra Island, Indonesia. We conducted 2.5 years ago. And here, this is a mountain area covered with tropical jungle like this. So we prepared a 5 kilometer long line source at the foot of the mountains by utilizing the agricultural roads. And we applied the current about 30 amperes. And we took the TEM data at 40 receiver points, and the covered area 6 kilometer by 6 kilometer. And this picture shows how to make the electrodes for line source with having a very low contact resistance, like this. So this picture shows how to set the sensor cluster. We just place on the ground. We don't have to dig the hole. So, and real-time judgment of data quality is possible. So typical measurement time is 2 hours per 1 point to taking the 1,000 cycle data acquisition. Okay, this is the 3D register structure obtained by 3D inversion, and this is one cross-section of 3D register structure. So this brown color or red color region has a very low resistance, resistivity, less than 10 ohm meter, and the depth is 500 meter to 1,500 meter in depth. And this low resistivity region possibly indicates the cap layer under which the geothermal reservoir exists. Okay, in this figure, we compare the one cross-section of a 3D register structure by skid TEM is compared with that obtained by a previous MT survey. So you can see it's clear. So a skid TEM gives a resistive structure with a higher resolution. And moreover, this low resistivity region agrees well with the thermal manifestation in this region. Next slide, please. Okay. Next example is exploration we conducted in Kyushu area in Japan, the near operating geothermal power plant. It's actually a brownfield. Here is a geothermal power plant generating 27 megawatt. And here is also pipelines and production wells, and also here is power transmission line like this. So we took the data, these measurement points. Okay, the biggest noises in such area is the noise come from the power lines, power transmission lines, and this is a low busy signals. So you can see a very large signal, it's a magnified image. This is actually 60 hertz signal from power transmission lines. So, but by filtering or carefully subtracting 60 hertz and higher harmonic signals, and after stacking 1,000 cycle data, the noise level becomes very small, about 1 picotesla, which is almost comparable to the speed sensor noise itself. Okay, concerning the influence of eddy current generated in the well casings and pipelines, we found that only the pipeline parallel to the line source have a significant influence on the magnetic field transient. But however, when we set the measuring point more than 300 meters far from such a pipeline, the influence can be minimized. So very, very small influence. And we also found the influence of well casing is negligible. Okay, this is a 3D resistivity structure obtained by 3D inversion. This is one cross section. So you can see this brown color region has a low resistivity less than 10 ohms. So this possibly indicates the cap layer of a geothermal reservoir. And here in the cross section, you can see the height difference in the east side and west side. This is because here a prominent fault exists. So I can't show all the data, but the geoelectrical structure we obtained by SCOOT-10 measurement consistent with the geological structure containing the faults. Okay, third example is exploration we conducted last autumn in the national park area, including a very famous volcano, Iwate-san. So in this survey, this is a commission by Jongme, and in this survey, we employed a high power transmitter and apply a 90 ampere current into a 6.5 kilometer line source. And the measurement points were also initially set near the summit of this mountain. It's actually the national park area, because we can get easily permission, because we don't have to dig the hole. But unfortunately, because of the raise of the volcanic alarm rate at that time, so measurement near the summit we abandoned. But instead, we added additional measurement points on the back side of the mountain, more than 10 kilometers far from this line source. And I can't talk about the detail of the results, but I show you one result. This is a 3D resistive structure obtained by inversion, 3D inversion. So now the expression depth is more than 5,000 meters, so we confirmed. So this indicates possible application or technology also to supercritical geothermal development. Okay, finally, I'd like to briefly talk about the monitoring injector fluid. So we tried in the Middle East countries. So there, the injection of seawater and CO2 fluid in the peritotite formation has been conducted to realize the mineralization. So in that area, we tried a time-lapse SCOOT-10 survey before and after injecting this fluid. Okay, and this is a cross-section of 3D resistivity structure obtained before injection. This is after injection. So after injection, you can see the very low resistivity region like this. And this is the conductance difference between the before and after fluid injection. So this gives a clearer image of plume of the injected fluid. So this actually is the presence of fluid plume and its direction of migration was validated by the fluid sampling at the monitoring well. So this result suggests the possibility of applying our technology to the monitoring, for example, for EGS. Okay, let me summarize my talk. By employing our recent SCOOT-10 system and the ground layer configuration, our exploration depth was extended to 3,000 meters to 5,000 meters. and a low-risk feed structure due to a geothermal reservoir with cap layer. Injected fluid in high-risk feed formation has been clearly detected by 3D inversion analysis with SquidTem data. And our SquidTem solution is expected to improve drilling success rate for geothermal development, both in green and brown fields. And our SquidTem solution could be applied to development or monitoring for EGS and supercritical geothermal power development. Okay, thank you very much for your attention.
So my company, we specialize in baseload renewable energy, mostly smaller size baseload 对不起，我讲国语的。我们公司主要在做的生意，主要都是基载型的小型绿电发电厂，那包含了地热发电跟沼气发电，跟这两种发电的各种各样的仪器跟数据分析跟诊断 ，OK， 所以真的就是这个小型的绿电发电厂。那这是我们我们的工作，我们公司2011年成立的时候，有点不顾正业，都是搞一些仪器啊、数据啊。后来我还是回到本行去做绿电。那其实我的强项是在这个沼气发电，我做了很多年的沼气发电。后来大概5年前，有一个意大利的朋友骗我说：“地热也很好啊，在台湾应该做地热。”那我就跳进这个地热行业来，然后发现了啥？这个地热水有够深的，你知道吗？不是一般人能够做的。那所以我们也还是一样，在第二方面，我们还是专注于电厂的这一部分，怎么提高电厂的稼动率，怎么提高电厂的这个效益。对，那这下面是我们所做的工作，包含了系统设计、代理，研发我们自己的一些工具，设备跟仪器，然后也有帮别人盖厂，也有帮别人做维运。然后呢，最后当然是我们有帮我们客人做一些财务上的协助，牵线，找银行啊、找投资人啊等等进来帮忙他们解决一些财务上的问题。然后这个下面就是我们所做的这个不同领域里面的这些不管是独家代理商啊，或者是我们自己开发的这个设备啊、产品啊，然后包含了地热、沼气，一堆很多的仪器啊，那这些仪器大部分都是跟振动分析有关，或者是跟电分析有关，或者跟水分析有关，及一些比较特殊的应用的东西。那我们也在，当然，因为你不可能一辈子当个代理商，说我们也在开发我们自己的产品跟自己的这些仪器。然后有这些仪器，有这些比较先进的设备的话，你会生产出很多的数据。那这个数据怎么利用？这数据其实是有价值的。所以我们就会去做，比如说远端监控，然后再用专家去帮忙做这些故障诊断。那我们现在是慢慢从原始的这个用人工的方式，原始这个人工的专家，慢慢把它智慧化，变成用 AI 的专家，AI 的工具去帮忙做诊断。那我接着谈一下我们这个在地热这方面的经验。我们在地热这边在台湾已经耕耘了差不多有5年左右，算是新手了。但是在这5年之中，从我们的客人身上学到了很多经验。OK， 那我这边就会谈一些基本的概念。OK， 怎么跳这个来了 ？OK， 好，那这张我就不讲，反正就是政府说我们台湾有很大的这个地热潜能啊等等，搞不好真的做完之后连电费都不用，就送给老百姓了。老百姓不用买电，你知道吧？因为钱就随便谈，就是40G 啊、60G 啊、100G 啊什么的，都很大的数字。那目前为止，台湾几个电厂产不到10枚，所以我们这个可发挥的空间、可努力的空间蛮大的。对我这个年纪人来讲，说是无限的。OK。那在这个地热开发的这个过程中呢，我们所发现到的一些问题是什么？但它的优势就是它是一个稳定的基载，它的这个能源密度，单位能源可以可以产蛮多的电，然后它对这个环境的影响真的非常小，比任何的燃烧方式 那燃烧当然是我的专长，比任何的燃烧方式的碳足迹都低。OK， 然后但是也有很多挑战，法令不清楚，这是一个很大的一个挑战。地的限制也是一个很大的挑战。你要随便找一个比较好用的地，可能就会碰到国家公园的问题，或者碰到原住民的问题。那这些政策跟人文东西，当然我就不知道，因为那个不是我的专长，我是个做技术的人。但是我所知道这些都是问题。然后团队的建立，那因为这个产业在台湾也算是第二了，那中原挖掘我不知道，但是针对第二的话，算是一个蛮新的产业，所以这个产业里面的专家跟人力够不够，这是一个很大的问题。对，然后开发的成本高，因为你刚开始嘛，所以当然成本就是很高啊，因为你都在研究啊，都在可能打很多水漂啊，做一些所谓的实验啊，所以你的成本一定会很高。所以大家要进这个第二产业，我想你要有心理准备。那这个不管是任何产业都是一样。我想当初台积电成立的时候也是花了很多冤枉钱，慢慢学会的。那我们现在第二也是一样，也就是慢慢大家说就是慢慢的去学会怎么挖一个有效的井，怎么去盖一个有效的电厂。然后目前为止呢，就是电厂的效益不如预期。那这其实电厂就是我们的专业了，我们公司专业。这张图是我跟我们合作的这个第二顾问公司 Steam 借来的。那他基本上谈的这个概念就是说，你前期的风险，就你在做第二案子的前期风险，探勘啊、测试井啊等等的，这个前期的风险相当高，但是你所要花的钱并不是很多，几百万、几千万，在第二里面根本就不是一回事。这百万、千万根本就不是一回事。只要你没有这个，你口袋不够深，没有这个钱的话，不要来玩地热，这不是你的游戏了，即使你是个小电厂，这也不是你的游戏，那你把前面的这些初步的探勘啊、地表的探勘啊，只要做好的话，你的 MT 实验做好了，或者像日本那个技术什么做好的话，那你就有可能可以去找人帮你写一个初步的可行性报告。那这可行性报告呢？你就可以去拿银行，可能有些比较勇敢的银行，或者勇敢的投资人就说，我这个初步调查已经做好了，我下面是有可能的，这个土地没什么问题，然后呢，地方的一些政治呢我也把它摆定了 ，OK， 所以就可以去做一些，有这个初步报告之后，可以去做一些融资的动作 ，OK， 那你可能就开始去挖井了，挖一个这个生产井啊。然后做一个产能测试啊，那只要这个产能测试做出来，还好，蛮漂亮的，水温啊、水量都存在的话 ，OK， 你的 PI 值就是你的生产指数看起来不错的话，当然你可以再去做一次融资，再去跟银行要更多的钱，说我还要再挖更多的井，因为我这个地方选对了，然后我的挖井队也很强，所以我要再做第二个井、第三个井、第四个井 ，OK， 所以就是一步一步来。那最后就是到了地表的话，那地表就是你知道，像我们这种搞发电厂的人，没什么风险了，你知道，那个东西都是很老的技术了，所以没什么风险，而且都是你看得到的东西，都是很成熟的技术，所以不要他去在意说这个地表要花很多钱，那个钱是可以马上回来的。特别是假如说你的趸售是7块3毛2的话，只要你的电厂盖，只要你前面这个工作做好的话，那个投资回报其实是蛮有可能的了，对，是蛮好的，对，所以电厂是我觉得应该是大家做第二里面，你的顾虑需要最低的地方，而是前面这边这些高风险的都是跟地底下你看不到的东西，这个对我们来讲是一个风险。只要大家能够了解这个的话，照这个步骤去走的话，我觉得你可以把你的风险跟你的产能会有一个比较好的一个管理，对。然后接下来是我们在台湾这个5年的经验里面，就是说一些学习的这个一个算是教育了哈，就是探勘这个阶段早热。那其实台湾有很多第二开发商都没有做自己的这个探勘，都是拿中油啊、工业院啊、什么单位、地调所什么那种30年前、40年的老资料，可能只是个前景的资料，就开挖了。那这个风险很大， 这风险很大，这个要小心这个。怎么有效的用最低的成本找到这个热源？那用旧资料只能做参考，你还是要做新资料，去找一些专家来，不管是做 MT 的或者是 Geothermal 什么的，反正就是找一些专家来帮你做这个地调，然后做一些分析。再来就是这个井，那井也不是随便一个洞，这井其实要设计的，你应该有一个挖井的一个计划，OK， 所以这个也是要找一些专业的挖井公司来帮你挖这个洞，OK， 而且不是一个洞哦，可能要好几个洞，OK， 那这个挖井的费用其实是蛮高的，OK， 你也不要说挖打一个水泡白挖了一个洞，那就很伤了，OK， 所以这个挖井井的设计跟这个挖井的话，其实也是蛮重要的。然后这个再就是很多人不会谈的就是说这个井的永续性跟寿命，就是它的这个 decay curve 会是长什么样子，OK， 很重要。因为你比方说你挖了一个井，它的寿命只有5年，那台电给你的这个合同是20年，那你剩下15年怎么办？再继续挖井吗？挖井很贵啊，所以井跟井之间怎么样互动，它的关联性、它的干扰怎么样 ？OK， 你井的里面你怎么去管控这个井，避免它过度严重结构，非常重要。很多井用没有井就挂了，为什么？结构。那从这个我这边讲的是什么？地热流体就是我们叫做 geoflow， 就是地热水了，或地热蒸汽了，这都是叫做地热流体。那它的这个化学特性你必须要了解，为什么？有结构的问题，有腐蚀的问题。那地热流体的这个压力，其实压力非常关键。你压力控制不好，只要你只有水的话，然后你压力控制不好了，开始散发的时候，你就会大量的结构，然后你那个结构的那个速度是很惊人的。OK， 所以你要去了解你地下有什么矿物质、镁啊、钙啊等等的，多少二氧化碳啊，然后是不是有可能会产蒸汽的这个机会？那去有这个结合之后，你就知道说，只要我的压力不管好的话，那个结构是不得了的。只要真的结构的话，你的井基本上是废了。这个流体的温度，那其实流体就还没那么关键，但主要就是我的要找的就是要高温的，温度越高，我发电机的效率就越好啊。卡诺定律很简单，OK。那再来就是你这个温度能不能够保住？因为假如说你的井没有挖好的话，可能井跟井之间有干扰的话，那你的温度就是往下掉了 ，OK。它能不能够达到一个平衡点不一定 ，OK。所以这上面都是跟挖井跟你的井有相关的。那这个我也是看了大家的案子，然后从中学习到说大家的这个痛点在哪里。所以我只是把我看到的这个痛点跟各位分享。那下面这些都是跟电厂比较相关的东西，就是说我们今天要发电的话，我们基本上都是在看 LCOE， 你发1度电要花多少钱？那当然影响它的就是你的固定投资跟你的操作成本 ，OK， 那就这两个东西 ，OK， 然后再来，相信我，你去跟银行贷款，然后你一直跟他争个什么1%、2%的那个利率啊，我跟你讲，那完全没有意义。最重要的是什么？你在这个地热电厂的你的井的服务团队跟你的电厂的服务团队能够给你多少的稼动率？你的电厂到底有多可靠 ？OK， 你一年可不可以有95%的稼动率？只要一年只有70几%、80几%的话，那在业界里面就叫笑话。OK， 你的目标最起码是最低应该是80%。再来就是你维运1年之后，你对整个厂都很熟之后，你的稼动率应该在90以上了，92啊、95%那种概念。OK， 所以稼动率非常重要。你唯一还债的这个能力，就是这个发电机必须要跑，它必须要能够给你发足够的电，你才有还债的能力。不然，只要你只是拿那10%的尾水去做一个温泉会馆的话，我保证你那个还不了什么钱了。对，所以重要的还是要还电啊，用电来还债。OK， 所以怎么确保说你的电厂能够永续的发电，非常非常重要。OK， 那当然这个不只是地热，任何电厂都一样，沼气电厂火力电厂都一样。 这个永续性，这个稳定性，这个稼动率非常非常重要。OK， 再来最后一个重点我要提的就是说，有些人会把这个系统啊，想说我需要加那个，把这个一个地热系统或者是一个电子系统搞得非常非常复杂。相信我是专门做旋转设备的。那在这个旋转设备里面呢，它这个会损坏的几率非常非常高。OK， 即使你选到一个很好的设备，它还是会有挂的可能性。所以在你的电厂里面，你应该去想说，我怎么把我电厂简易化，用最少的设备达到最高的稳定性、最高的稼动率。你越加越多，你电厂就会越容易挂掉。OK， 除非你备料一大堆，那备料就是现金啊。对，你愿意花这种钱去买这些备料的话 ，OK。但是假如说你只有一个2枚的电厂，你要备多少备料？你今天是一个200枚的电厂，那不一样了，对不对？那概念不一样，那经营规模不一样了。所以这个我们叫做把电厂设计的越简单，对你的维运、对你的电厂的可靠性就越好。那我来介绍我们现在公司代理的几个产品 ，Thank you。那第一个就是我们有跟这个代理这个俄罗斯公司叫做 Novomed， 它大概是全世界做这个整水棒，不管是油井用的或者是地热水用的，大概是第一品牌吧。然后这个跟看那个不是 Haliburton，OK， 他讲的这个结构是完全一样的。下面就是感应器啊，马达。保护器跟水泵 ，OK， 任何的盛水泵都是同一个概念。但是呢，我们跟盛水泵呢的说明书可能70-80页，这说明书里面70-80页呢，就是让你去选，依据你的地球化学、你的地球物理、依据你的温度、压力等等，怎么去选这里面的材料 ，OK， 让这个能够最适合你的这个井的特性 ，OK。让你能够让这个盛水泵在下去的时候有最好的寿命，因为知道盛水泵下去的时候，要出来的时候只有死掉挂掉之后再出来，不可能说拿盛水泵然后搬出来再修啊什么这些的，没有这回事，因为这个下去上来的这个费用非常高，所以就是把我们叫做use to fail，OK， 就是把它用到它挂为止 ，OK。当然挂之前是不是有些征兆说它要挂？有，你必须要懂怎么去看它。对，那所以你需要很多的参数，去这个 monitor， 去监视这个设备。对，那我们有2种这个马达，那这个马达是大概在一个电水方面作为挂的东西。那我们有一个叫做感应式的，一个叫做永值式的。那你很明显看到说这个永值式的呢，它的效率也比较高，然后它的从高负载到低负载的都能维持一定的这个效率，所以这个很重要，因为这个效率就是电。你要多少的内耗电，就是要把这些设备选好。哦，对不起，我这边再讲一下，就是因为他们用了泳池，所以温度可以耐很高，流量可以蛮大的 ，OK， 然后经验也放到很深很深，油井里面放到6公里去了 ，OK。然后这个是我们现在在台湾的一些主要在选的一些机型，那我们台湾已经卖了2只这个 ，OK， 等一下会介绍。那我们就是然后现在在谈的都是一些比较大的，因为我们在鼓励大家，你做地热的话，井就是要挖大，你挖一个7寸井做地热意义真的不大，要做就是把它洞挖大，水量大，因为地热就是水，你水量不够的话，你就不用玩了。OK， 那这是我们在台湾的某个暗场 ，OK， 我们原始的这个生产值大概是1个小时10吨到20吨左右，装了传感棒之后。我们达到了110吨，对，那原本这个10吨20吨呢就是没有经济效益的，对，你装到100多吨的话，那2只加起来差不多200吨，那你就有经济效益了。然后这个厂就发差不多1枚左右。然后这个是讲我们的这个地热发电机这个 ORC， 那这个公司08年成立之后呢，它专心做比较小的这个 ORC 发电机。那全球安装数量是在小型那个 ORC 发电机里面是排名第1位的。OK， 那这个我就不讲了，反正就是一个典型的 ORC 的循环，这我就不讲了。OK， 那它现在这些都是比较旧的机型，这个150、200，它最大发电就是200千瓦， 然后我们做了一个水冷式的，把三台组合在一起，在一个40的货柜里面，那它最大发电量是600千瓦。那现在今年要出来的就是这个新机组就是可以到2000千瓦，就单机2000千瓦 ，OK。然后这是几个，这个是我们在今年我们一共有4台像这样子的，那一台里面就是有3个 ORC， 差不多最大发电量是600千瓦。那我们现在正在推的是这个比较大型的，对。那老外也很听话，我就跟他讲说，好，谢谢。我们台湾的地方小，路小，山坡多，你拿一个40的进去很困难，所以我们现在就把它全部改成用20的方式去把它拼装出来的。对，那我们在这个台湾的这个实际，也就是也是在金轮 ，OK， 在台东这边卖了2场1枚的。我这边这就是另外就我想要谈就是说，这种案子其实也不容易，蛮难的，有很多的技术面的东西必须要考虑，所以一定是用一个团队的方式去做这个案子 ，OK， 所以不可能是就是一家单家独斗，这个不可能的事情，水真的很深。好，谢谢。
Usually my presentation are different. This is why organizer either put me as a keynote speaker or the last one. So being the last one, I appreciate you all coming here. Thank you very much. Before we start to talk about this, I will tell you several things. First of all, at the end of this presentation, I would like you all to understand that Inogia, a French company which I'm consulting recently, has developed something which is a little bit new and different idea of improving the utilization and efficiency of the geothermal power plant with the technologies they have, but also with the understanding of the concept of the whole solution. And talking about understanding the whole solution, I will try to summarize a full day seminar I'm giving to students into 2 or 3 slides. I would like to start with explaining to you what is going on in the markets that we are in, which is the electrical market. Because if we don't have the wide scope, it's very easy to it's very hard to focus on where we can benefit. So we are right now in the middle of a revolution of the electrical market, or the energy market generally. We used to have the old traditional grid with huge power plant pushing everything into the consumer one way, and it is gone. The introduction of the renewable energy, the diversification of the production, the liberalization of the markets are changing the way we are doing business. Today, and especially tomorrow, what the market is going through is a concept of microgrid and energy community. You will hear more and more talks about energy community, about a group of people with common denominator of energy production, energy consuming, and how we can help them to make sure that we are keeping diversity, efficiency, and resilience to our customers. You'll see this in a moment. The smart grid collects different kind of production and take in consideration the other side, which can also contribute to that. It's not anymore one way. It are both ways, and very interestingly, more and more the electrical car becoming a player there as a storage source. Think of it, it's again very wide variant of it. I would like to pay attention for you for 2 things. First of all, we are trying to eliminate on the old school of the fossil fuel. Nuclear is here, kept and living, but not the old huge nuclear facilities, but we're talking about a small nuclear reactor, what we call generation type 5 and type 6. It is here. You will meet it more and more because this, plus the geothermal small modular ORC, are going to be the pillar of this new smart grid. They're going to be the base load. because all the rest of them are not baseload, and you need to equalize and stabilize the network. Okay? So, geothermal is a true baseload and can replace or enhance wherever is applicable. Unfortunately, you can do a geothermal power plant only where there is geothermal. Yes, we all talk about AGS and EGS, and definitely it's going to be valid solution sometime in the future when it will be also commercially available. We are getting closer and closer to that, but we are not there yet today. Of course, the uncertainty is until the first production well. There are a lot of talk about this. I will not stay too long about this. We don't have too much time. Except for a rare case, ORC is the technology for geothermal. You will not find today a real flash system, definitely not double flash system, utilized in a geothermal area. Okay, in New Zealand, which was the biggest area of double flash, you don't find it anymore. They're going for ORCs, some of them big ORCs like Ormat Sinatamariki and others like that. Iceland is one of the only places where you can really find a good steam that can operate a big geothermal power plant in a reasonable economical structure. So what we're talking about today is about an energy community, we're talking about efficiency, diversification, and resilience, and we are talking about how geothermal is a core pillar to support this kind of structure, which is the future structure of the electrical market. When we are drilling, and when we are investing in well, the highest cost investment and highest risk, what we would like is to have efficiency. We would like to have as much as possible for what Mother Earth gives us. And according to the depth and the temperature, we are going to have a lot of applications. It's not only electricity, and it is wrong to think that if we have geothermal, what we should do is electricity. No, what we should do is make an efficient combination solution to what we are doing. Okay, I'm just putting here as a start the MED, the MED desalination process, which can be very easily supported by geothermal for island cases where they need fresh water, agriculture, or potable. Okay, this is a very interesting solution. I'm pushing this for quite a while with the Greek islands, which have a real problem. But I don't know, I guess in Taiwan you have enough fresh water, you don't have this issue, but it's also one of the applications for the geothermal. Okay, so when we are developing a geothermal place, a geothermal resource, we would like to prefer a multi-application solution. We like to maximize the efficiency of that. We like to involve and support the local communities. It is crucial, again, to think of the big picture. You are coming and you are drilling and you are building a power plant. It's not anymore a huge power plant somewhere where the government says, forget everything, this is the land for us and so on. No, those are small power plants that are next to the communities that they use them. And you find a lot of rejection because it was not explained, it is not educated, it is not brought properly to the communities, they don't understand the benefit. And part of the efforts that companies like Inogia, like Turboden, like Ormat are taking in consideration. I know for sure, I mean, I less know about Turboden, but I know Ormat for 20 years I was working there. I know Inogia as a consultant. Community must be taken in consideration when you are developing a geothermal power plant. You have to maintain the resource control. If you are not maintaining your resource, your geothermal power plant will, or geothermal project will not work properly, and you have to minimize the environmental disturbance. All right? So, we also know each well is different. Therefore, each well has to be considered for the multi-application, for the efficiency, a little bit differently. And you need the knowledge and the expertise to do that. And every well most likely can provide a multi-application. So you can do this. But in order to do this, it must be agreed and designed before. If you do not know this, if you don't take this in consideration when you are building a geothermal power plant, you might find yourself afterwards with something that is not
going to be exactly what is needed. Not what the customer wanted, but what the customer needed. There is a difference between the two. Very briefly, what you can expect on the project execution as far as time and more or less average cost in every phase of it. What I want to say in this slide is developing a geothermal project is a multidiscipline, quite expensive until it is working. Once it is working, it's a honey bunny. As one of my Turkish customers used to say, I'm sitting with my legs up and just rolling the dollars like that. Once it is running. So if it is properly designed ahead of time, it is properly executed, this is the best solution that you can get. This presentation will be available afterwards to everybody, so you can read more of that. So what have we developed in Enosia to suit the needs or the black holes that we found together on the geothermal market? Okay, in a moment I will tell you why the Enosia solution suits them. But we found two areas where you can quite easily do more with what you have or what you are about to have. One is what we call topping. In many cases, you have existing wells serving existing applications where the temperature is above what you need. District heating, you need about between 75 to 95 degrees to support the district heating. Wells, I've seen in Iceland wells that are 125 degrees. For the district heating, they are cooling. They have a pool to cool the brine from 125 to 95 or 90 or 85, whatever they need, to suit the needs of the district heating. Guys, you just wasted 5 megawatt of electricity here. You know? This is something that exists and it's very easy. It's a very smooth plug-in into existing geothermal systems. You just put there a unit on top of the well, take what it is, and instead of them just cooling it, make electricity out of it. True for the onsens that we've seen all over Japan, you know, and spa facilities. Again, Ormat has a beautiful solution like this in Austria, in Bad Blumau, where you have a well that is supporting about 200 kilowatt of electricity to the hotel, from their district heating, from there to the spa. This is the best efficient solution I've seen in the world until now. We are offering something like that, very easy to implement, and of course immediately join the multi-application. Why also it's important, I'm not sure about here, but at least in the EU, sites that have multi-application gain incentive from the European Commission. So in October 22, the European Commission changed the regulation over there, and you can get incentives for being efficient. It's also important, money is also important. The second solution that we found amazingly suitable for the Enosia solution and a hole in the geothermal project is what we call a single wellhead solution. There are cases where you have already a well which either doesn't provide to you what you are expecting from the total field, or it's the only wells you can drill there. If you drill another well, they are dry, or that this well has been drilled and now it's going to take you another 3 years until you finish drilling all the other wells in order to support a bigger unit. And what do you do with this well? Well, you invested a lot of money there. You can generate electricity meanwhile or together with, and those cases are very clear. We have also cases in oil and gas where gas wells are there and you are extracting hot water with gas and you are wasting the hot water over there. It's another solution for a single wellhead solution. That means you're taking a well and you're just putting one unit on top of the wellhead. You are saving a lot of gathering system cost, okay? And you are starting to produce electricity much faster, or even if it was not even considered before, on something that you already invested. Okay? So today, when introducing Enosia into the geothermal field, we are coming with two concepts. which has to be examined case by case, like you have to do always with a geothermal project, for either topping solution or a single wellhead solution. All right? Now I'm focusing more into why Inogia. And this is where I'm starting my sales pitch. Till now it was marketing. It was like me being a teacher or lecturer in the university, what I do recently. For me, the best RC solution that exists in the market, I'm sorry, door number 3, okay? Are the large one. If you're talking about a large RC solution, it is Ormat. And we know Ormat has excellent solutions, let's say 10 megawatt and above. And if you talk about small ones, it's the Inogia. This is an example of Inogia 1 megawatt. Containerized and very easily implemented in the field. Okay? So, again, looking at each project by itself and the project phase, personally, I think you should go to either one of them. But that's my opinion. You may have a different one. What is the technology to match the application needs of Inogia? Okay? This is some samples. This is one of the more interesting ones that I've seen from them. And again, when I retired from Ormat after 20 years over there, and they asked me to consult them, and I saw it for the first time, I felt like, wow, this is what the part that was needed to complete the picture. We're talking about a closed, capsulated, patented turbine and generator. We're talking about a very small turbine, high speed, capsulated in something like that size, okay, with the generator inside, with the multi-fluid inside. Nothing comes in and out except the heat coming in with and the electricity coming out from the generator. All this is containerized with heat exchanger, with a pump, and with a little bit of electrical control, of course. It has a modular approach. You can put many units one next to the other. You have several sizes. We'll see it in a moment. It's a very small footprint. Nothing is coming out of it. It's excellent to implement in area where you have nature reserve or much more environmental concerns. It is very fast in implementation because it's all containerized, capsulated, containerized at the manufacturing site, delivered to the site. If all the civil works are ready, if all the connections for the resource are ready, you're talking about a few days of implementation and start to operate. And Inogia solution can start generate electricity at a temperature of 75 degrees. And this is what was mentioned before when Sam was here in the morning and says, what would you do with wells that are 100 degrees, 110 degrees, which, those of you who have seen this in the morning, what will we do with them? You will generate electricity with them. And you will design the solutions that it will give you district heating at 75 degrees or at 80 degrees, but you still generate electricity from them. You have a solution for a lower temperature, an economical solution, a valid solution, and a proven solution, because Inogia has more than 200 sites over 30 countries around the world, not all of them, very few in geothermal, most of them in other areas, but this is where you have it. And this is the center of one of the solutions, this is another one of the solutions, another one just to see. I'll briefly go over that again, you will be able to see that. What are the key values? The company numbers. It's a small company. It's been recently published, became public on the French stock exchange. It will be a big one, believe me. But today it's a small one. This is the current range of solutions they have. Biggest one is a single unit, 200 kilowatt. But in a recent application that they are doing in South Korea, we're talking about a 10 megawatt unit, that means 25 units on a fuel cell solution, which is distributed along the same area but in several places. Another solution, part of the concept of being independent, each one of them. This is the turbine and the generator. There's a picture just to show you what is the size of the. This is the size of my hand. So this is more or less the size of the unit, just so you can understand what we're talking about. It's different. You didn't see such a thing before. Currently, three approaches to the supply to the market. You can either get only the ORC with the skid, you can get it with the dry cooler, or you can get it all containerized. The reason for these three stages is because in many cases, if you do it locally, it will be cheaper. Okay, so definitely you will not do this locally, but if you want to do other parts of it locally, it will be cheaper. And this is by thinking of the end user at the end of this. Where we are today, what are the references that we see, different sites. Again, you'll see. In geothermal specifically, you can see some of the solutions here. In this case, the air cooler is part of the container. And to summarize in a nutshell, to help you remember, and we have also a one-pager over there, you can go and look at it. We are talking about increasing the utilization and the efficiency of projects of geothermal by either doing a topping solution or a single wellhead solution. Remember those phrases because they will be part of your future vocabulary. Topping means taking the high level of the temperature of what is already existing, plugging in there, the generator or a single wellhead. Okay, who is up? She told me time is up. All right, thank you very much.